Yeah, your kiss here.
Hello and welcome to All Space Considered, everyone. I'm Dr. David Reitzel, and All Space Considered is brought to you by the Department of Recreation and Parks of the City of Los Angeles. And we also like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. We have a great show for you tonight. And on our panel tonight, we have Laura May is with us, Laura May Abram, Ginger Rose Brucker, and Jared Head are our panelists. And All Space Considered is the third Thursday of every month. And tonight is Thursday, September 18th. And come on up. We do the show live from the Leonard Nimoy Event Horizon Theater. So if you want to join us at Griffith Observatory, you can. Or you can watch us, of course, on YouTube if you'd like to watch us at home. And we thank our remote audience as well. Tonight we have a really fun show. We have news about the Grand Canyon and dark skies. We have Bennu samples reveal a dynamic past. There was a smash up at Venus. When did this happen? We'll find out. Perseverance and ancient life on Mars. Maybe you heard about that story. We'll have Jared talk about out to launch, some things that have been thrown out into space and how they went. Is the sun made of Italian food? If only, right? I don't know why that stuck around, but I liked it. Astrophotography with Ginger, new title for our section, picked by Ginger herself. Hooray, thank you. A dusty star-shredding black hole. We're going to talk about a story where a star got shredded by a black hole. And then gravitational wave detector confirms Einstein and Hawking. Einstein confirmed yet again. Yeah, I know. How often is it? He's proven wrong once or twice. There have been a couple of times, but Einstein's been right. And that leads us into our special guest tonight, Dr. Gabriele, it's Vajente, right? Vajente, yes. To get that correct, he's the Deputy Head of Systems Science and Engineering at LIGO, and that's the Laser Interferometry Gravitational Wave Observatory Laboratory. That's the place that finds the shaking of space itself when black holes merge. So we have the expert here to talk about the 10-year anniversary of the first detection of gravitational waves and what we've learned in those 10 years and what they are, and you'll have a chance to ask some questions. It'll be great. So thank you, everybody. It'll be a great show. Well, to start our show tonight, I want to talk about that background image. This is an image that was supplied by NASA to celebrate the 6,000th exoplanet that's been found. We have found 6,007, actually, planets around other stars. So when I was a kid, I used to watch Star Trek, and I'd think about all those planets that were out there, that people could be wandering around on alien life and things, and I wanted to know, when are we going to find that first planet around another star? Well, we did finally in 1991, and till today, we are over 6,000, and there's something like 5,000 more ready to be confirmed in the TESS catalog. They're going to confirm many, many more of them. So we are just scratching the surface of how many are out there, and it's a very, very exciting time for science and astronomy to have that many exoplanets out there. So we'll talk more about them later, but it's a monumental number, really.
And coming up to 30 years, too. It'll be it'll be 30 years of 51 Peg B.
50 Peg, yeah.
So the hot Jupiter found around the main sequence star.
Yeah. Well, Laura May, you just recently came back from the Grand Canyon to join us tonight.
Correct. So I'm just here for a couple of hours, currently living at the Grand Canyon and working as the astronomer in residence there. This is a program that was started in 2021, and it's supported by the Grand Canyon Conservancy. Now, I do want to ask our audience a question. So who here has seen the Milky Way quite like this?
Okay.
Right, a couple of you.
Yeah.
We are in an observatory, so it doesn't totally surprise me. Now, if I offer you a trip to the City of Lights, Paris, or to the Grand Canyon, for example, where you can see the Milky Way, who picks Paris? A couple of you.
Baguette, anyone?
That's, you know.
That's the Americans thing.
Who picks the Grand Canyon Milky Way? All right, quite a few. All right, it's a good data sample since we're in a city but in an observatory. So not too far from here is this place where you can see the Milky Way at the Grand Canyon. And in fact, that is why we say half the park is after dark. This is an illustration by Tyler Nordgren, who was a previous astronomer in residence. Now, How good is the sky there? So this is a scale that you're seeing that was created in 2001 to rate the brightness of a night sky in any location. And the Grand Canyon is a Bortle 1 out of 9. So you can see at 1 we've got really beautiful transparent skies, and at 9, 8 it's just really very light polluted. But long before this classification even existed, the astronomer and telescope maker George Ritchie became enamored with the Grand Canyon, and he drew up plans to build the world's greatest astronomical observatory there. So here's an image he took that was superimposed with a drawing created by an architect on a cliff that doesn't exist. And this observatory would have been about 250 feet tall. Again, right on the rim of the canyon. A set of movable, adjustable mirrors larger than the 200-inch, for example, the one down in Palomar, and with statues and columns of Greek or Roman temple. Obviously, financing, I'm not quite sure he had all of that figured out. But George Ellery Hale, whom he used to work with, and who founded Mount Wilson Observatory, Yerkes, and Caltech, so they had a falling out. And it seems that he panicked a little bit upon hearing of these plans. There were a lot of publications, especially at the time Ritchie worked for Paris Observatory, so he announced these plans in France in June 1928. There were publications in the New York Times. And so George Ellery Hale sent Edwin Hubble to assess the conditions of the Grand Canyon. And this trip actually delayed, most likely, the publication of his results on the expansion of the universe. So a fairly interesting, But long story short, of course, it was never built. There was no real advantage to building right on the rim, but there's a lot of reasons not to, right? If any of you have ever been to the Grand Canyon, you'll know the air is pretty turbulent due to all the bottom of the canyon being much hotter. You get all of that hot air rising, and it's confined by cliffs, which creates not so great seeing, blurry images. It's also very dusty. And so eventually, Ritchie ended up building a telescope in Washington, D.C. for the U.S. Naval Observatory, and he was then moved to Flagstaff. So he did get somewhat of a telescope near the Grand Canyon. But soon after that, the architect Mary Coulter, she was one of the first recognized female architects in the United States, she actually designed the 70-foot tall Desert View watchtower that you can see nowadays if you go there. And she thought of it as a Native American astronomical observatory. It was also inspired by the Puebloan towers. And the top floor was maybe supposed to have telescopes. And there are murals inside of the tower that show the Hopi cosmos. So was it inspired by Ritchie's plan? This started being built very shortly after his announcements, and so she must have known about it. But so the Grand Canyon continued to have strong ties to astronomy and space. In fact, it became a training ground for astronauts. So here is a historic shot taken in 1964. Some of you may recognize this man, first person who ever walked on the moon, Neil Armstrong. Here he is on the Grand Canyon South Rim. Lowell Observatory, by the way, Kevin Schindler has a great talk about this. And it took until 2019, the 100th anniversary of the park, to certify it as an international dark sky site. And by the way, this is a huge, huge effort. So here's a screenshot from the GIS, or the Geographical Information System layers, that they actually developed, and they inventoried all 5,200 lights in the entire park. So in green, those are the ones that have already been retrofitted. In red, those are still to be worked on. And again, we're talking absolutely everywhere, in the canyon, on trails, everywhere in the park. And now the national park has reached about 91.5% compliance. So they have until 2029 to reach the last 10%, which means the skies there will only get darker. And here is an unedited shot I took just a few days ago next to one of the visitor centers, just to show you really how the sky looks to the naked eye. So this is what you see when you just walk outside of any hotel and restaurant, and you can kind of see the Milky Way there towards the bottom of the image on the left. And in fact, it's so dark that they were able to see the northern lights over the canyon last year during the Gannon storm back in May. So this photo, in fact, was taken by the Dark Sky Project manager, Matt Young, and it shows The aurora is reflected in the Colorado River. If you look
Wow.
right down at the bottom of the image,
That's amazing.
really incredible to see this. So this allowed them to reach 80,000 people in 2024 with their dark sky programs through about 354 informal and formal astronomy offerings. This is one of the talks that I give over there. And this is inside the visitor center.
Wait, it's science fiction to
science.
space. This is where we talk about jaw red and your science fiction names.
That's right.
Everyone's got a science fiction name here.
We all have our science fiction names.
So you can consult the astronomy and night sky program on their website all year long. Of course, you can consult it right now to see some of the programs that I'm running there. But they also host the largest star party in the United States, maybe in the world. I'm trying to get figures. I tried to find figures from other places, but it is 8 nights in a row in the summertime, and they had over 80 telescopes and 10,000 people.
And what are the little dashed dotted lines in the sky there?
Satellites,
Satellites.
Unfortunately.
Yeah.
It's actually quite hard. I took a couple shots to, not this one isn't my picture, but it was hard to get some shots without the satellites, especially, of course, the Starlink that are very
They're
long
more
on
and
the
more
horizon.
common, and anyway, I was surprised that maybe I'm not supposed to talk about that, but in that hearing they had in Congress about the lights that they can't explain, some of those are obviously Starlink satellites. It's like, come on, Congress, go talk to Mike West. He's a dude on YouTube.
And they do look quite strange sometimes.
It's
I've
almost
seen
like
some, but
it's just crazy how
it's not aliens.
they don't actually care to go talk to experts that know about this stuff. They just anyway.
You're kidding.
Anyway, carry on.
But the nearby city of Flagstaff, for anyone who's visited, they started a similar process much earlier. So in 1958, they actually enacted the world's first outdoor lighting ordinance with strict regulations put in place to reduce outdoor light pollution. And so they became the world's first international dark sky city in 2001. Pretty incredible.
Cool. Now wait, go back to the
Nice.
sign.
So they've got a lot. They've got America's
that's-
first, I think, first STEM community. I kind of
That's
wondered
cool.
what that was.
Actually does.
Specific.
Science, technology, engineering, math. So it's
But
very cool.
I'm not sure
Why they're the first.
Why they're the first.
I don't know, but that's great.
I guess they have the
Yeah.
university.
They got the sign up
There's
first.
that
The sign up. That's right.
Yeah.
And of course, they have Flagstaff has Lowell Observatory, where Pluto was discovered, and that really is. You can see from the city. You can walk around in the city and just see the Milky Way like this.
Yeah.
But don't they have glow-in-the-dark sidewalks?
They do.
too?
We
So
saw
you
them
can-
together.
Yes,
in
that's
fact,
right.
they have really beautiful glow-in-the-dark sidewalks. They've really
Super fun.
put a lot of effort in. And in fact, more broadly, Arizona is also a hotbed for astronomy. It has the largest number of optical research telescopes in the U.S., and globally, it is one of the top locations for astronomy. Now, Hawaii has more large telescope concentrated on one site, but overall, Arizona has a greater total number of optical research telescopes that are spread across multiple mountains.
Kip Peak, Mount
Kip
Graham.
Peak, Mount Graham, Mount
Yep,
Lemmon.
Mount Lemmon.
They also have radio and submillimeter observatories. And of course, unfortunately, all of this is at risk. So light pollution is not getting better. So while the dark skies of the Grand Canyon are getting darker, everywhere else is getting brighter. In fact, the recent studies have shown that globally, skies are getting 10% brighter on average each year, globally. I had to verify this figure. I didn't think that was actually possible, that they would be that much. And in fact, the previous astronomer in residence, Stephen Hummels, he took measurements that assessed that light glow doubled between 2015 and 2025, which is...
Does it peak out at like full solar day?
I
Is
think
where
we're just
they're
trying
going?
to have eternal
I don't know.
daytime. So the studies are starting to show that not just effects on wildlife, of course, plants, but also humans. We're starting to link, it's a little bit difficult, exposure to light pollution to various types of illness, mental health issues, neurodegenerative diseases, and it also, of course, has environmental and financial costs, right? So you can consult these online maps. There are a couple of them. You can go to, I think, lightpollutionmaps.com or .info. And we're pretty lucky here because the western half of the United States is much better than the eastern half. And the most light polluted place in the world is Brussels and Belgium and the entire Netherlands area. I don't know what they're doing there.
Not LA?
Not LA, surprisingly. And of course, the cause is the global increase in artificial lights and the shift to energy efficient but blue-rich LED technology, which scatters a lot more light in the atmosphere. So retrofitting lights is, for example, one of the easiest things that people can do, as well as switching to warmer LEDs. And you can get involved with local initiatives. You know, this is how they did this.
Put the light where you need it as well. When you're beaming it up into the sky, you're not putting it where you need it at all. There's been studies that show folks out and about in cities that are sort of more dimly lit and evenly lit create a lot less light pollution in the sky, and it's safer.
Yeah.
When your eyes actually dark adapt, you can see into dark corners. You can see in places where there could be somebody hiding.
Yeah, it's true,
I don't
the
want to scare
contrast.
people, but the contrast on bright LA city streets, if you're under a bright street light, you look down a dark alley, it just looks dark. If you're in a moderately lit place, your eyes will be able to see better.
Adapted
So
better.
there's
Lots
been
of-
studies all about this that
Yep.
show there's more safety in the dark than you think.
Yep. So I hope, all of you can at some point visit the Grand Canyon or perhaps Death Valley, which is also nearby, which has a good dark sky. And just imagine if we could have this in Los Angeles. We could.
Yeah.
And there is currently.
Yeah, well, we have right now there's an LA park survey you can fill out. The draft park
Needs assessment.
Needs assessment
Yeah.
is what the NA
NA.
is. And everybody can go fill that out. And it's really to fill out whatever you want your parks to be. So if you appreciate Griffith Observatory, you can talk about, hey, I want more Griffith Observatory. If you think you need more soccer fields, go talk about we want more soccer fields for the kids to go play soccer like you see in the picture here. But the parks want us telling the public about it. So this is actually our 90th anniversary feature. Every month we do a little brief thing to acknowledge that Griffith Observatory is in our 90th year. And for our 90th year, I want our public to connect with the parks and to tell the parks what you want from it. And I hope you say, we love Griffith Observatory, we want more observatory things. It's come to us. But also, our parks are important, and there is a need. Los Angeles is sort of park deprived in certain areas. They've made these little pocket parks where you can go and get some, take your kid or do something. But a lot of them aren't safe. They put in equipment. The equipment gets destroyed almost immediately because there's no security. So there are issues that you may care about that are very important to you. And I just want to acknowledge that. So you have things you want to talk about and say, hey, why don't I have a park within 5 miles of me or 3 miles of me?
Yeah.
That's an issue. And that's what this survey's there for.
And they've been very receptive. I've attended several of the hearings. There are only 50 people on the last one out of a city of 4 million people.
Yeah, so find out when the
connect.
hearings are, attend if you care about parks. Parks are important for community, for our lives, for our kids, clean spaces. It's just
and you can
it
email
brings
in
the city to
comments
life.
as well.
Yep,
So just
email in
email
comments.
comment.
You don't have to go in person. So, well, turning the page here a little bit, there's an asteroid called Bennu, and indeed, this is the weird shape it has. It's sort of this weird rubble pile.
Square.
And it turns out, because of the spin, little boulders will fall down from the top and sort of roll down more towards the middle. It's why it has that shape. This shape is caused by the spin, but indeed you're seeing big boulders on there. Well, we sent a spacecraft, OSIRIS-REx, to go grab some material off of Bennu. And we did, and here comes, I love this video. I mean, how often do you get to see material grabbed off the surface of an asteroid?
Like a little punch.
But notice some of the material is bright white. So there's little white chunks in there. There's dark chunks. The material have different colors. I think, was it Bennu or Ryugu that had a piece of Vesta on it, the asteroid Vesta. I forget which it was. But material has been transferred from one object to another, and the asteroid belt is a very confused place. So grabbing a sample, which here's the samples after they were returned to Earth in the sample container there, being analyzed, and it suggests that the various materials from the parent asteroid, Bennu had a parent asteroid. It's a rubble pile assembled after a bigger object got smashed apart. That bigger object had water on it, and that water was influencing and changing the mineralogy of Bennu. So, kind of crazy. Now, what's even crazier is they discovered a huge number of, it's the chemicals that can lead, the organic chemicals that can lead towards amino acids. And those amino acids are the things that go into things like, DNA and RNA. So they found a whole bunch of the chemicals that life needs. They found ammonia, which can react with, I'm forgetting what other chemical, but they found both of the chemicals that can react in to create even more amino acids. So what is this telling us? It's telling us that the early solar system had all the materials that needed to make life. So could it be common? Could there be life elsewhere in the solar system? Maybe. This is why we study these objects. We want to go to them and say, what are the raw materials they're like? Bennu was evolved. It went through a process. It was destroyed, part of a bigger object got destroyed. But still, even through all that chaos, we can say, the materials for life are there. If you build a planet like Earth, out of a whole bunch of Bennus. So maybe that's the way it went down. We're not really sure. But impact melting played a role on this as well. The impact itself that destroyed it melted some of these things, so we see evidence of that. It's a rather complicated, like I said, a smashed up story on Bennu, that it went through a complicated process. So this is crucial for decoding and figuring out our history, the solar system history, by preserving these early materials and analyzing them. So there's a new one they want to launch to go visit Apophis in 2029. It'll be called Osiris Apex. So stay tuned for that, and hopefully that mission will get funded and be sent out there, because it'll be fantastic. Another object that may have had a smash up is Venus.
Yeah. So our beautiful neighbor Venus may have had an impact in its youth. Now, the early solar system was very turbulent, with lots of objects forming through collisions, of course. And the early, and of course we had our own moon, which came most likely from a collision with an object called Theia, which smashed into the Earth about 4.5 billion years ago. And we had a recent study that investigated whether a giant impact in Venus's early history could explain two of its oddities. Now those are, number one, it has no moon, and number two, it has a very strange rotation. So here you're seeing a little illustration from our very own Chris Butler, who made this very quickly. What you're seeing is the fact that Venus, on a day on Venus, is actually longer than its year. So what we mean by that, of course, is that the Earth's rotation, that's 23 hours, 56 minutes, whereas Venus, it's 243 days. And it's also a retrograde rotation, not an astrology term. It means it orbits in the opposite direction to the other planets, right? So what they did was they ran smooth particle hydrodynamics, simulations of possible impact scenarios, and so they tried varied impact angles for your impactor coming from this angle or this angle. And with impactors that were about 0.01 to 0.1 Earth masses, so much smaller. And they found quite a few impact scenarios that can produce a post-impact spin rotation period that's quite similar to what we have now on Venus. And typically they didn't create large, stable debris disk outside of what we call the synchronous orbit. And that means that most of the debris would have ended up falling back onto the planet. Hence, we don't have any moon there, even though big collisions do tend to produce satellites. So an impact like this would also inject a lot of energy, possibly affecting Venus's internal and thermal evolution. So the thermal profile and the existing rotation state prior to impact, that's something that's a little bit uncertain, that will probably require more studies. But almost the same week that this paper was released, there was also a study on how the Mars quakes, so we are currently measuring Mars quakes on the red planet, and they might be showing that there are lumps inside of its interior that accumulated from past collisions. So some fairly interesting, simulations and information on our early solar system and all the collisions that would have happened. So, women may be from Venus and men are maybe from Mars, but both planets might share a common story of being redefined by impacts.
Yeah.
I'm testing out my jokes here. This book is a little too old, so it didn't quite land. It's an old book.
Hopefully it doesn't trigger anyone. Mars, indeed, suffered all sorts of impacts, and the fact that you can see them down under the surface in those earthquakes, fascinating stuff. Well, we have a rover cruising around on the surface, in fact, a couple of them. And one of those rovers is in Jezero Crater, which is over on the right there. And let's zoom in. This is the surface of Mars, by the way, a map where we dragged it out all into a flat map like that. Projected, I forget the name of the projection. But we zoom in here, boom, there we are. And you can see Jezero Crater's over in the purple, in the lower, a little bit to the lower right. They've named some other craters there. And it's an interesting region. You can see it looks like there's some cracks up there. Is there sort of, well, what's going on? Let's zoom in. Oh, now it's really interesting. This is the crater itself. Notice in the upper left, sort of around the 9:30 part of the clock, if we turn that circle into a clock, there's an inlet. You can see it looks like a river flowed into this crater. And then over on the right-hand side, you can see there's an outlet where the crater was filled with water, and the water flowed out over there and created another output, a little river there that carved. That is definitely signs of moisture on Mars. There's the target region where we wanted to send Perseverance when we sent it to Mars, and it landed pretty much very close to the center. They did a great job. But why? Why do they want to go there? Well, look, there's a delta where that river dumped into the crater. There are clays and carbonate minerals there. And you think if there's life, maybe the life got buried, or signs of the life got buried in those clays and in the minerals. Maybe it got locked up in some rocks. Maybe there was enough water there a long enough time that you could get some bacteria cranking along doing some stuff. That's why we went there. Curiosity, by the way, told us Mars once was wet. Mars once had the chemicals there for life to exist. Everything you need is there. That was what that mission was to do. Perseverance was to go look for locations and take samples that could show signs of life. Doesn't have the chemistry set on board, doesn't have the ability to prove it itself, but maybe. And in fact, at a location, you can see where the little area there is in the Neriva Vallis, in the little river valley there was a rock called Shayava Falls. And here's our Perseverance rover looking down at the rock. Looking up, you can see the rock has that little drill spot in it. Let's zoom in on the rock. A couple of spots in the upper right, you see that white disc, looks like a disc. That's where it polished the rock to see what it looked like underneath. And over on the left, it did another little polishing spot, and it took a core sample. That's that hole that's there. Why did it take a core sample? Let's look at this. About a year ago, a little more, I think it was July 2024, in fact, around there.
Yep.
I talked about this. We called them leopard spots. In between these sort of, looks like carbonate layers in there were weird spots. Okay, alamine crystal as well, but that might have been brought there in floods or in rivers, we think. But in between, there's this thing called a leopard spot. Those leopard spots on Earth are made by bacteria. The bacteria is using the chemicals present, converting them, extracting energy, and leaving a slightly different chemical behind. So it's a chemical process. Well, recently, there's a paper in Nature released, published, I should say, where they analyzed those chemicals. And the chemicals are what would be there if it was life that made this. Now, they're careful to say, oh, hey, maybe there's other ways to do it. One, you could have really, really hot, acidic water. Problem is, we don't see any signs of acid with these rocks. We don't see any signs of the type of heat with these rocks. So one way we know to make these things, yeah, it's not there. So when in a sort of more temperate water that maybe we could, you pick up, wouldn't hurt us. What? Yeah, life. That's the most likely explanation we can think of at the moment. So life on Mars, maybe. Now, where are we on this chart? This is a chart of super excited at the top. Yay, we found life outside of Earth. And on the bottom is, oh, there's something interesting. So first you detect something you can't explain easily. And then you got to go up and confirm and rule out other sources, rule out contamination. Well, we flew a rover to Mars and drove up to a rock and drilled into it. So contamination we could kind of rule out. We're seeing it right there in the rock. The next level up, it's, well, I can't read this, my eyes are too bad. Anyway, it's trying to find the detection of the biological samples, saying, do you see the chemicals that would be left behind by biology? Yeah, that's where we're seeing. So we're up to level 3 now. Level 4, all other possible biological, all known non-biological processes could be accounted for. We haven't done that yet. We can throw away the hot water one and the acid, but maybe there are other ways to make this stuff.
And there's chemistry that we may not know about.
That we don't know about, maybe. So right there's where this starts to break down. So how could we prove it? How could we go higher up? Take a sample. Here's the sample that Perseverance took. You look down in the sample, there are leopard spots in there if you look carefully. We've got a perfectly good sample on Mars, ready to be picked up, that we could bring back to Earth and analyze and say, yeah, that was life that made that, or no, it was made in some other way. We just have to go get it. And where is it? It's right
not
there.
Too far.
There it is.
Not too far. It's on Mars, hanging out at the little red dot. Now, Perseverance has moved on to the end here. You can see it's driven on from that location. Each of these red exclamation points is another sample it took. It's up to 27 now, I believe. This was the 25th sample that has the leopard spots. They're lying there. In the last proposed presidential budget, the mission to go get those samples was canceled. So, however, most people think a lot of this will be put back in. Congress does their part. Remember, this is a process. But I'm just saying, if you happen to like this idea, this sample that has these perhaps signs of life on Mars sitting there, and you want to bring it back, well, you know what to do. I don't know.
Start a GoFundMe.
Start a GoFundMe.
Yes.
Let's.
If you've got $20 billion,
I've got some
we can make it happen.
Well, maybe what'll get us going is if the Chinese say, "Well, we'll go get it, we'll analyze it, and we'll let you know what's in there." Maybe.
Except that we
happen.
just forbid, I guess,
Well,
collaboration.
no, but I'm saying they'll do it on their own.
Oh, sure.
Yeah, they don't need us. Well,
Yeah.
they do right now, but they won't in the future.
I think they have they have a sample return that's already planned, I think, for early 2030s, so
Yeah.
they don't really care
Yeah.
what we're doing.
They don't care what we're doing, but we've got the sample that we know is interesting. Now, there's probably more samples that are interesting, but I like Perseverance here being like, well, what you gonna do? I got it for you. What do you think? So anyway, exciting things on Mars, and another exciting thing, we have Jim Bell, who's on this paper, lined up to talk to us. Now, we don't know whether he'll be a guest in person next month
Zoom,
or
maybe,
over
who
Zoom,
knows?
maybe. He's at Arizona State, so it'd be quite a drive, although you took the bus, so. Jim, you hear us? Come on down. Anyway, but stay tuned, check our website. It'll be a really exciting talk, and we can ask him all the hard questions about these samples, the chemistry, what he feels, how confident are they, all the rest. Because this is the most excited I've been about life on Mars since the Bowie song.
Since the Bill Clinton announcement?
Yeah, since the Bill Clinton announcement. Yeah.
Or 97?
Well, but even that one, I still am not convinced isn't possible. The AHL, the Allen Hills meteorite, and I forget the number, but there's some weird stuff in there.
Yeah.
Anyway, well, Jared, we've got an out to launch tonight.
Yeah, we've got a few launches to talk about,
terrific.
actually. So let's just go ahead and get started with them. This is the CRS-33 mission. So this was a cargo Dragon that was launched mid-August. And this is a particularly special cargo Dragon because it is getting ready to do something that Dragon has not done yet. And I'll talk about that in just a second.
Fire.
So, yeah. Well, I think it's doing a good job there.
It is doing a good job there.
Because the engines are Merlin's, I guess Merlin is helping the Dragon out a little bit there. So,
I see
some
what you did
crossing mythology. I don't know. So, a beautiful launch that they had. And then I love this from our friends at Sen, who now have these amazing 4K cameras that you can access for live streams on the space station. This amazingly beautiful footage of this crew Dragon, or cargo Dragon, on approach to the International Space Station, getting ready to dock. It's just...
Are these running all the time or only for special?
They are running all the time.
Wow.
So you can jump online and take a look at
spy.
them.
Yeah.
So, and it's just
awesome.
gorgeous
Very
to be able to look
sci-fi.
at this. Yeah. And also their YouTube channel is pretty great too. They do like a weekly recap of the best things they've seen.
Sweet.
So that's a time lapse. It doesn't
So
actually
smooth.
hit that hard. We still have to worry about mass and other things like that. But the reason this Dragon is so special is because of what's in its trunk. So, and that, goes for some folks, but also this is what's in its trunk, which, you said Jiffy Pop earlier.
Yeah.
Like, it's taking popcorn up there. Well, not quite. These are propellant tanks. And then the black tank in the middle is a pressurant tank to have that propellant come out. And what this cargo Dragon is going to do is it's actually going to fire its engines to help boost the International Space Station.
Right, 'cause
So Roscosmos, Russia's space agency, is not flying as many Progress cargo vehicles to the space station, and that is what was primarily providing the fuel to the thrusters on the space station that would boost it. But they're not flying as many, so now NASA has asked SpaceX to sort of step in and see if they can do this, and this is a test on this mission to see if they actually can do that.
Yeah.
And it's also...
So they're not going to make popcorn?
No, unfortunately, unfortunately not. But if it was, I'd want it to be extra butter, right?
Okay,
like, let's
delicious.
get that.
Does the orbit just decay, obviously, over time?
Yes, so a lot of people don't know that even at the altitude of the International Space Station, there is still technically things like atmospheric oxygen and other things up there.
Yeah.
And you're running into that at 5 miles a second, 8 kilometers a second. So because of that, there is drag on the International Space Station, and it will lose its orbital altitude if you don't maintain it. So you have to fire engines to do that. So every couple of weeks, they usually will fire the thrusters on the space station. There's really cool videos of that where the astronauts will put a camera with a long telephoto lens inside of a module let go, and then you can watch it accelerate as it's not, touching anything as the space station goes higher in its orbit. So it's pretty cool.
Do you know if it's also affected by ionospheric expansion from solar maximum?
Is. Absolutely is. Yeah, the density of the atmosphere is 100% with what the sun is up to. So, and as you can imagine, lately the sun has been a bit
fussy.
Yeah, a bit fussy, tough to work with. So it's kind of helped out. But another interesting thing that this does is that SpaceX is contracted to do the vehicle that will bring down the International Space Station at the end of its life. So this is looked at as a test of that. And then also they're going to do a what they call Dragon XL, which is a special version of Cargo Dragon, which will help bring cargo to the Lunar Gateway Station. And this is also considered a test of the propulsion system that should help with that as well.
Well, the Lunar Gateway is anyway, don't get me
What
started.
year is the ISS coming? 2030s?
It depends on which member of Congress you ask at the moment. So we'll find out in this year's budget, at some point, I guess. But this wasn't the only thing. In late August, guess what actually happened? They launched the Starship Super Heavy from SpaceX, and it worked.
It didn't blow up?
It didn't. Sorry, hold on. We do have something to talk about a little bit later in the flight here. But this was nice to see that SpaceX is kind of coming back from that. Flight 8 didn't really go so well. They lost control of it very early on. Flight 9, something ruptured, and they lost control of it on re-entry, and it did that. And then when they were testing the original Starship that was actually going to do Flight 10, it blew up, and it destroyed their test site, which isn't good. But they were able to fix it in time, and they actually set it up so that their launch pad would be where they could test it at, and then quickly switched it back so that it would be a launch pad. So, beautiful shot of those 33 Raptor engines at the bottom of the Super Heavy booster starting up. You can see that they're stagger starts, so that way the energy acoustics of coming off of the engines don't basically tear apart the bottom of the rocket, and then going up nice and slowly there. And as an engineer, I just look at this and that's what I want. Yeah, that's the good stuff right there, let me tell you.
Do you have any marshmallows?
That's what I live for.
Yeah,
marshmallows?
Yeah.
I was going to say,
failure.
It's a little hotter than it is outside right now down there. So, but it is drier, so it's not humid in that area, I can tell you that. We also had the successful hot staging from the Starship, which is basically Starship, the upper stage, turns its engines on while it's still attached to the Super Heavy booster, and then Super Heavy, while still firing its engines, sort of pitches back, although I don't know what to call it. I really like the turn and burn, but also I think flip and dip might work well for it too, because it flips and then dips out of it. So I don't know. You'll also notice in the bottom left corner that there was an engine out, and they were testing engine out capability on this. They actually did have an engine not intentionally not work correctly, and not just for the return, but for the actual landing burn as well for Super Heavy. They had Super Heavy come down, and something like about 200 to 250 meters above the Gulf of Mexico, they had it hover, and then they turned the engines off and let it fall into the ocean. And this is a view of that there. You can see it's hovering. Now the engines are off, and here comes the booster into the ocean. Whee! It's going to be fine, right? No, it wasn't. So yeah, we lost camera from that really quickly. Whoops! Searching for the cameras. But those cameras inside of the Starship upper stage vehicle were working really well. They actually tested out deploying some Starlink simulators. So these are supposed to be the size of the next generation Starlink satellites. And my favorite deployment was this one, because watch this Starlink simulator as it goes out. Don't hit it. Bonk. Oh, man. It hit it. It's kind of reminded me, if you guys are Star Wars fans in A New Hope, when they're breaking in to try to get C-3PO and R2-D2 with the stormtroopers, there's a stormtrooper in the background that hits his head on the wall. That's what that reminded me of. So I was like, it's just got stormtroopers on there. They wanted to test the actual engines on the upper stage. So this is what a engine burn looks like in space if you've never seen one before. So lots of dynamic flow happening there. And then eventually it was time for re-entry. So one of the harder things that Starship has had to deal with. So what you're seeing there is plasma that is being developed as the vehicle goes through the Earth's atmosphere, compresses the molecules that make up our atmosphere and make them super hot. And we're talking temperatures up to 3,500 degrees Fahrenheit here. So this is pretty hot. And this is one of the aerosurfaces that they have on there, and we'll actually take a look at it a little bit later too, because we were watching this live in real time. So this is some amazing stuff. We've never really watched atmospheric reentry in real time from the actual vehicle itself. So this is always a treat to see this. But I asked you to kind of hold your applause a little bit earlier, because as we were watching the reentry here, everybody was like, yes, it's working. Everything's going perfectly, just like it should. Oh, maybe not.
Oh, no.
So, obviously a event, as it was described, happened. We still don't know what actually happened with this. SpaceX hasn't said, but hopefully before their next flight, Flight 11, which should be sometime towards the end of this month or beginning of October, we'll find out a little bit more. But, just taking a look at some more of the plasma dynamics coming off of it. This is at the top of the Starship looking down, absolutely beautiful views there. And just like I'm thinking about just running in the air that fast, making it that hot. And also this view as well, which we'll see that aerosurface in the back there, actually. And a lot of people thought that event had caused what you're seeing on the edge of that aerosurface right there, which is not good. You
That
can
looks
see
like a
material
remove before flight tag.
Yeah, that if it was, they forgot about it.
Yeah.
But it turns out in photos that were taken before launch by a couple people, they actually intentionally did not put heat shield tiles in that area. They wanted to see if the actual aerosurface would hold. And this was done because they were really pushing Starship on this atmospheric entry. And then here's the landing burn of Starship. You could see different colors on Starship because different types of tiles were being tested. So we think that this is the orange is metallic tiles, and then the white one up towards the top are actually tiles that may be using a medium like water or something to actually be used to cool down. So not much heard from SpaceX yet in terms of that, other than pretty successful flight there, an absolutely beautiful image of it coming down.
Yeah, finished with a rainbow there.
Yeah, you got to if you're gonna fly big, right? That's a good way to do it. Now this one was just last week, which was the launch of NG-23, which is a cargo vehicle that Northrop Grumman has developed, and they are currently not flying it on their own rocket, Antares, because the original version of Antares used engines and materials that were built by a supplier from Ukraine. So obviously that is not a thing anymore. Northrop Grumman is working on their own at the moment, and they bought several flights from SpaceX to do that. Just kind of showing this footage here because the tracking cameras this day were absolutely on point. So this is, like 100 miles away, and we're seeing the upper stage and the first stage booster like separate perfectly from each other there, and it's absolutely gorgeous to be able to see that. And then I wanted to show this because if you've never seen one of these in person, I highly recommend you go out to Vandenberg Space Force Base to see it. This is what a landing looks like for a SpaceX booster from the beginning of the entry burn. Wow. So we could see this rectangular pattern of exhaust from 3 engines firing, and then it'll go down to a circle because it's 1, and then they turn off. And it kind of, the booster's a little hot, so you got some smoke there. And it's continuing to come down. We can see on the left side there the speed and the altitude, so it's not exactly coming in slowly. And if you do go see one of these in person, you do get loud sonic booms. And it is spectacular. Because out at Vandenberg, if you're standing at the right place, it really does feel like it's coming down on you like this.
I get a call from my mom every time one goes off.
Yeah, yeah, me too. So now you can see it's really coming in through the atmosphere. Now it's at about the height that an airliner flies at, and we're really starting to see that friction build up. And then it's going to light that center engine and come on down. And again, the tracking cameras on this as an engineer, hats off to those people. This is like the footage that I want to be able to go back and look at my vehicle.
Well, yeah, the altitude here is 5 kilometers up in the air still. This is incredible footage.
Yeah, it's unbelievable. And just like watching it come down and seeing the shocking of the atmosphere, having the moisture come out like that, it's just astonishing. Man, I want a camera like this. Where do I get one of these? So
a camera or a rocket?
Yes.
Exactly.
Both. You're just
yeah, I'll take it. This will definitely get me to here at the observatory a lot faster.
Yeah, it's true.
So,
traffic days.
Yeah. And that is your out to lunch.
Yeah. Well, thank you, Jared.
Appreciate
it. Fantastic. Well, it seems like we can't go a month without something exciting happening on the sun. And maybe it's because there's so many observatories observing the sun
It's true.
So it's great. It's fantastic.
And we have, in fact, let me turn on my clicker. We have, of course, again, DKIST strikes again. So the Daniel K. Inouye Solar Telescope, which is in Hawaii, has been bringing us these incredible images with its 4.24 meter primary mirror. Pretty exceptional. So, for example, we have this recent sunspot image. So this is a colder region on the sun. What you're seeing is a sunspot, and the filaments that you're seeing extending out are basically the manifestation of the magnetic fields. So, and we now have this incredible image of solar pizza. Phenomena.
Wow.
So what you're looking at, let's see if our little video plays. So you're seeing the closest ever image of a solar flare, right? This is really, really remarkable. This is an X-class flare. It was a 1.3. So this is the most powerful type, or the most powerful class of flares that we have. And this is the closest ever image of a solar flare. So this, for example, is to show you what it looks like when we get the entire sun. This is shown in extreme ultraviolet. And I actually placed the Earth right next to it to show you its size, just for comparison. Whereas this is our scale, basically, so it's about 4 Earth size in that image, right? So this is a different wavelength. This is in hydrogen alpha, and pretty remarkable that we can see these kinds of details. So what you're seeing on there are basically what we call coronal loops. Coronal loop strands. So we're seeing just incredible detail here. And these are arches of plasma that follow the sun's magnetic field lines. And they usually will precede solar flares that trigger these sudden releases of energy that are associated with some of these magnetic field lines twisting and snapping. So really, really cool image. And by the way, this measured loop is about 48.2 kilometers. That's 30 miles, right?
Just crazy.
Again, that's really, really small. Some are even half that size. And keep in mind, the sun is 900,000 miles or 1.4 million kilometers. So the fact that we can start resolving structures that are about that small is pretty remarkable. And also it's important because it gives us breakthroughs in determining the fundamental scales of coronal loops and advancing our modeling for solar flares, right? So this is really important. In fact, we were just talking about it with regards to satellites and the ISS. We want to improve forecasting for space weather. Solar flares affect us on Earth. It's hazardous to satellites, power grids, communications. So the more work they do, the more close up we can see the sun, the more we're able to kind of predict and have really good models for what's happening when we get solar flare and then potentially a coronal mass ejection. So really amazing stuff.
Yeah, very cool. Well, thank you. Ginger, what do you have for us tonight?
All right.
Yeah, we get some.
So this month.
Thank you, Laura May.
Thank you. We do have some sun pictures coming up,
Excellent.
so we will circle back with that. All right, so our first image here is a James Webb Telescope image. So you'll see there's kind of a theme here because last month I picked the tarantula nebula, and now we're to butterfly in the sky.
Okay.
This was taken on August 29th. And this space butterfly lives about 525 light years away within the Taurus constellation. So as you'll see these huge disks, which are about 65 billion kilometers, or about 40 billion miles. So it's about several times the diameter of our whole solar system, which is pretty cool. And it's just a beautiful image. Okay. And then, of course, a tiger butterfly in flight at Griffith Park. I saw this in the LA Times and just thought it was very nice to show.
Amazing photo.
And then we have a Hubble surveys a cloudy cluster taken on September 8th. And this scene is in the Large Magellanic Cloud, which the Tarantula Nebula actually is in, and it's in the southern hemisphere, of course. So this is just the largest star-forming region, which is called N11, I mean. And this is the most massive and prolific star-forming region in Large Magellanic Cloud. Next up, we have another James Webb image here. So, glittering glimpse of the Starbirth from NASA's Webb Telescope. And this was uploaded on September 4th. And you can see right there, and just like those stars in the middle. So it's a star-forming region called Pismis 24. Actually, I didn't know much about this region. It's a very young cluster, and it's in the Lobster Nebula, which I also did not know. And there was a lobster nebula?
Every single animal exists as a nebula.
Lobster,
yeah. And this is 5,500 light years away in the constellation Scorpius. So pretty credible image in detail. Then the next image is another James Webb stellar jets on the outskirts of our Milky Way. And this was uploaded on September 10th. So these jets are actually moving at hundreds of thousands of miles per hour. You can kind of see it. It reminds me of Star Wars. They're stretching all that way. It's about 8 light years of space. So twice the distance between our sun and the next nearest star, Alpha Centauri system. And then we have, I don't know if we have showed this yet, but the Curiosity views a Martian rock shaped like coral. And this was uploaded on August 4th. And of course, the Curiosity Mars rover, they were able to get this stunning image here of this coral piece on Mars.
But let's be careful. It's not coral.
No, it's not coral, but it looks like it.
But it's caused as water interacts with the sand there, a lot like structures you can see in our own deserts.
Yeah.
Form that way.
Yeah.
You can even make them.
You can.
So, yeah.
What's the size on it?
It's about 2 inches.
Oh,
yeah, so it's not
little.
Yeah, it's not actual coral. And we do have a comet. This was on September 14th. This is Comet Swan 25b. And you can see the tail is about 2.5 degrees, and which would be if you took 5 full moons and you put it across, so pretty good. And then we have Spica up there in the right corner. So the International Astronomical Union actually estimates that this comet will have its closest approach around October 12th, 19th, around then.
Any chance of naked eye visibility?
I think the sun, unfortunately, is going to be in the way, but it is right next to Mars in the Virgo constellation right now. So sunrise around then, yeah. And then here is another image that we have of it, super beautiful. And then we did have a lunar eclipse from September 7th. Did anyone here see it by any chance? Anyone traveling?
Not visible in the Americas.
Not visible here.
On the other side of the Earth.
Exactly.
Saw a stream.
Yes. And then we have our famous, of course, David Pinsky, the solar images.
Oh, we weren't going to show any Pinsky tonight.
Oh, wait, are we moving on? Where's Pinsky?
Pinsky's not here.
He's not here with us tonight. So Pinsky,
right.
where are you? We miss you.
We need you to interpret the sun.
And then
some beautiful prominences.
Yeah, incredible, actually, especially on the right side. All right, so one of our producers on the show, Daniel Perea, actually went up to Lassen National Park, and he was on a hike and went to one of the cinder cones up there. So fun fact, the cinder cone is both the official name of this volcano and a specific type of volcano. So this is just part of the trail going up to it.
Wow.
I love cinder cones.
Have any of you been there? You've been there?
Not that one.
I've been to Pisgah out in Mojave. But
it's like geyser that all the other geysers are named after in Iceland.
And then here is the actual cinder cone itself. So, and if you look to the right, you can see Lassen Peak. Fun fact, Lassen Volcanic National Park is one of the few places in the world where all 4 types of volcanoes can be found. So it would be cinder cones, you have shield volcanoes, plug domes, and then stratovolcanoes.
Cool. Wow.
And then this moon shot I just thought was incredible, rising over KS Craigs. Oop, skipped one. So I wanted to throw this in as like what is in the sky this month in September. So we do know that Saturn is visible all of this month. And then tomorrow there will be a conjunction between the moon, Venus, and Regulus. So you can just see them right there after another. And on the 22nd, we have the autumnal equinox. So, yay. That's the first official day of fall.
Yep, we're still in summer, everybody.
We're still in summer.
You can feel that.
Yes. And then another astrophotography image. This is the North American Nebula. I took this on September 2nd, and I used a modified camera. So we're seeing a lot of the hydrogen regions there. And you might ask, okay, what is a modified camera? It just means that the infrared filter has been removed. So the primary function of that infrared filter is to block the infrared light, but however, we want it here so that we can pick up those colors. And this area of the sky, I think, covers more than 4 times the size of the full moon. So, you can
Where did
imagine.
you shoot this from?
This was up near Santa Barbara.
Oh, yeah.
Yeah. And then we got this International Space Station Sprite. This was on July 3rd, 2025, and this was from a U.S. astronaut, Nicole Ayers, who captured this. Pretty incredible, huge storm. And then we have the X-ray radio go hand in hand. This was NASA's Chandra X-ray Observatory. And near the center of this image lies pulsar B1509-58.
Sounds like a nice place to visit.
That's a great place.
It's my favorite band.
Yes, it looks like an album cover, actually.
Yeah.
They covered B-52s. Sorry.
Yeah.
I'm glad you're laughing at
right.
least.
Well, thank you for all these beautiful pictures,
Yeah, of
Ginger.
course.
Yeah, we're running a
Thank
little
you.
late on the show, but thank you.
Yeah.
Let's give a round of applause for Ginger. I want to talk very quickly about this story. The James Webb Space Telescope was used to confirm that some black holes had eaten some stars. I know, kind of strange to think of it that way. Well, if a star gets too close to a black hole, it'll actually get shredded and torn apart. And the NEOWISE mission, it was a small infrared satellite that was up here, was studying some galaxies, and it saw some very short bursts of infrared radiation. And they thought, well, what were those from? And they thought, could they have been caused by a star being shredded by a black hole like this? You get too close to this black hole, you're shredded, and you give off light. Well, they're shrouded in dust. So that light is going into that dusty environment and creating a burst of infrared light. Wow. And then it went away, and they thought, well, what could that be? That's consistent with what we'd expect to see. But how can we confirm it? How can we be sure? Well, they used the Webb telescope to go back and look, and they took spectra of these galaxies, and they actually looked for neon. They were looking for doubly ionized neon. A star being shredded like that, interacting with dust, will actually doubly ionize the neon. And these are neon signs. If you remember those, you can still see them somewhere, some places. And if you take that neon and pass it through a prism, it makes that spectrum on the right. It glows. And notice there's a lot of glowing orange and red. Well, doubly ionized neon will actually have a different signature than that neon just bulb glowing, but they were able to recognize it and knew what they were looking at. And that was the prediction that you'd see that neon if there had been a shredded star, and they saw it in 4 galaxies that they looked at. So indeed, the NEOWISE mission, that little satellite, was picking up shredded stars being shredded, and the Webb telescope was able to confirm it with its capabilities to make some infrared spectra out of it. So again, when you have these advancements in technology, you're able to pick up more and more and more. And speaking of advancements in technology, this is this month's MOSTest. What happens if 2 black holes get too close to one another? Anybody know? Well, they can actually merge, and they can give off gravitational waves. So we're going to talk about that tonight with our guest, but these 2 black holes are orbiting. They're giving off this strange stuff happening to space. Very, very strange. So let me get my numbers, because this was actually an important, a first that happened. And let's listen to it. Let's go forward so you can see. This is the first detection ever, 10 years ago. Hear the little, we'll do it again. Here's the old one. Here's the new one. See how much quieter it is? Let's rerun that. So 10 years ago is the first one, and there's that a loud rumble you'll hear, and a little bit of a whoop in there. Loud rumble. There it was. See how much quieter it is and how much brighter the signal is? That's the improvement of the technology. The technology has moved forward, and we're going to hear about that tonight. Now these black holes, when they merged, this increase of the technology, this lower level of noise, they were able to pick up different harmonics in the waves that came off. And we'll see it here in this little animation. It picked up the first harmonic. That'll be shown here in just a minute. Here they come. They're merging. The waves are there, and now some things happen. So we're doing a little cut. There's the first tone, the first harmonic. The second one, notice the lobes are on the left and right versus being centered. And then the third tone is down buried in there, and those move outwards. Because of the high resolution and the quality of the signal and the low noise, they were able to pick up all three of those for the first time ever. So these are the sorts of predictions that were made. Einstein predicted this, and Hawking made a prediction that when you have a merger of two, the surface area of the event horizon of the black holes has to be the same or bigger than the surface area of the two black holes that merged. And it turns out it was true. So let me get the numbers here. The two black holes that merged, one was 32 solar masses, one was 33. When they merged, the resulting black hole was 61 solar masses. Some of the mass was lost in that gravitational wave, or the gravitational radiation that's given off. Now, one of the black holes had a size of 240,000 square kilometers. That was the two black holes together, before they merged. After they merged, 400,000 square kilometers. That's what the numbers had to be based to get these sorts of waves out of it. So Hawking, proven right. That was one of the things he predicted, that black holes, when they merge, the surface area needs to be the same or get bigger. It's sort of an entropy-related thing. Black holes are, entropy works with them too, and entropy has to go up, and the surface area is a kind of a measurement of that entropy. So amazing results coming from LIGO. And tonight, we have a very special guest. So come on up and join us tonight. Round of applause for our guest, Gabriele. Thank you so much for joining us. And we can switch over to your laptop. And you were here a little over a year ago with us.
That's about right.
But improvements have happened. Things have changed a little bit. But you're going to take a little bit of time to talk about some of the background on here. So we'll switch over to that laptop. Our crew on it. I can push the button. Here we go. So welcome, thank you so much for joining us, and let's hear about the dark side of the universe here. Thank you so much.
Thank you for the introduction.
Yeah.
Thank you for having me.
Well, let me introduce you properly. You come from Caltech, from the LIGO laboratory there, and you're one of the engineers. In fact, you're the lead engineer that keeps all of this running, so you know the details of how all this works. But you're there to see all the science rolling off the instrument as well. And how long have you been at LIGO?
I've been at LIGO 13 years now.
Okay.
So started as a postdoc, then a staff scientist, and now I'm the deputy chief engineer, so in charge of making sure that the instrument works and gets better and better, so we can see farther and farther into the universe and learn more and more.
Yeah. Now, well, I'll let you tell about it, but these instruments are amazing. This has opened up a whole new realm of the universe to study the universe in a new way. So how do we do it? Let's hear about it.
That's exactly what I want to talk about tonight. So tonight I would like to tell you all a story, and this is a story of the discovery of gravitational waves. It's a story of gravitational waves, so their discovery, of the instrument and the people that allowed this discovery to happen. So you might say that this is only a story that is 10 years old, because that's how long ago we have detected the very first gravitational wave signal. But actually this goes back way, way more in the past. It goes back many billion years ago, even before life existed on Earth, when two stars exhausted the nuclear fuel in their core and they went supernova. So there was nothing to stop gravity to collapse those stars. Nothing can stop that. And so everything collapsed into a single point and created what is called a black hole. It's a black hole because nothing, not even light, can escape from that. So there were two stars, and they both became supernova, and they both created black holes. We don't know if those two stars were already orbiting each other, or if they were separated and then the two black holes captured. But what happens when the two black holes orbit around each other is that they deform space and time. Black holes are so heavy that they create deformation of space and time. And as they're moving around, they create ripples in space and time. Think like when you throw a stone into a pond, you have those waves propagating a wave. the same thing was happening. So as the two black holes were orbiting around each other, they were generating these gravitational waves, the ripples in space and time, and they carry away energy with them. And so the two black holes are losing energy, and they're getting closer and closer to each other. As they get closer and closer, they move faster, faster, and faster. And eventually, they merge and they create one bigger black hole, just as you were explaining, right? So we were able, 10 years ago, to detect for the first time the gravitational waves of those two black holes. So those two stars were born billions and billions of years ago, and about 1.2 billion years ago, they collided. They created those gravitational waves that travel through a big chunk of the universe, more than 1 billion light years. And then also on September 14, 2015, those gravitational waves cross Earth. So gravitational wave stretches and squeezes things, like you see in this animation. This is a little bit on exaggeration. Nobody should be worried. We're not stretched or squeezed that much by anything. But still, that's the effect that gravitational waves do. They stretch and squeeze things. But this is an effect extremely small. So our detectors are about 4 kilometers long, 2.5 miles. Even over that distance, the effect was so small that we would have to zoom into a hydrogen atom, like you see there, go all the way to the proton in the nucleus of the atom, and the change of distance over 4 kilometers, 2.5 miles, is about 1,000th of the size of a proton.
Oh, wow.
To give you an idea of how complicated this measurement is, this is like looking at the distance between here and Proxima Centauri and being able to see a change of that distance like the thickness of your hair. So that's a very difficult measurement. Wow. That's why Albert Einstein predicted the existence of gravitational waves back in 1915, and it took us, humans, not me personally, but more than 100 years to detect the gravitational waves. And this is a way we like to show what happens. So the top there shows you, as time passes, the signal that we got out from the very first collision. So the purple curve there shows a lot of wiggles and noise. That's the background noise of our detector, that low rumble that we were hearing earlier. But then you see as time passes and you go to the right, there's that oscillation, that wave building up. And it's getting stronger and stronger because the two black holes are getting closer and closer, and they deform space-time more and more. And it's also getting faster and faster. The peaks get closer in time because the black holes are really spinning around 100 times per second. So imagine something which is 30 times the mass of our sun spinning around each other 100 times per second. That's mind-blowing to think that something like that can happen. So it just so happens that in January this year, we detected another gravitational wave signal from the collision of two black holes that were almost exactly the same, very similar masses, very similar distance. But look at the bottom line. Look at how much smaller that all those wiggles are. Yeah. So this is a testament of the hard work of hundreds of scientists and engineers that over 10 years just scratched their head and figure out how can we make this detector better. And by making this detector better, as you were saying, we were able to see these signals with unprecedented sensitivity and precision, to the point where we were able to see all those ring downs, as we call it, the black holes after they collided, and to prove more that general relativity is correct, and a lot of the prediction by Einstein and Stephen Hawking were correct. So we make our detectors better, not only to have more to see farther out in the universe, but also to be able to see the same thing better, to see more details. So that was pretty exciting, but something even more exciting happened a few years later. So when stars die and they collapse, if they're really big, nothing can stop gravity. Gravity wins over everything and you get a black hole. But if the stars are just medium-sized, a little bit bigger than our sun, but not very big stars, then when gravity squeezes everything down, the gravity will squeeze the electrons into the nuclei of the atoms. The electrons will smash into the protons and create neutrons. And you get something which is called, with a lot of fantasy, a neutron star. It's a big ball made of neutrons. Think about 1.5 times the mass of our sun squeezed down in something which is maybe 10 miles in radius.
Yeah.
So that thing is so dense that a tablespoon of that will weigh as much as Mount Everest. But the exciting thing is that we saw two such neutron stars orbiting around each other and generating gravitational waves. We saw the gravitational waves from those two neutron stars. But why is this way more exciting than black holes? Because, black holes are black, as the name says. Neutron stars are gigantic atomic nuclei. So when they smash into each other, we expected to see a big nuclear explosion. And indeed, that's exactly what we saw. So we first saw the signal from gravitational waves, and then the Fermi satellite, which is a telescope in orbit around Earth that is able to detect gamma ray bursts, so very energetic photons, very energetic light, saw a little blip, what is called a short gamma ray burst. So for the first time, we could connect really and prove that short gamma ray bursts are generated by the collision of two neutron stars. But it's even more exciting than that, because the gravitational wave observation allowed us to pinpoint in the sky fairly precisely where those two objects collided. And so, quite literally, half of the astronomers in the world just jumped on the car and drove to the telescope. At least this is how I picture them, just speeding up a mountain
like
to
in
get
Contact.
to the telescope. Yes, I love that movie, by the way. It's one of the best. But literally, more than half of the observatories were trying to find the counterpart, because you expect after such a big explosion to have a big cloud of gas, superheated. And indeed, the SWAP collaboration found that for the first time, 10 hours after the collision. The 10 hours was due to search all the galaxies in that patch of the sky and find the right one. Then the Hubble Space Telescope jumped in and gave us this beautiful image of the host galaxy. And you can see in the square on the main image the little dot that wasn't there just before the collision. And in the zoomed in insert there, you see that as time passes, day after day, it gets dimmer and dimmer and dimmer. And that's exactly what you expect. After a big explosion, the cloud of gas would get cooler and cooler and dissipates. But even more than that, astronomers can look at the color of that light using what is called spectrography. So you can see that as time passes, the color of the light and the electromagnetic radiation emitted gets from blue, which means very hot, to red, that means cooler. But also, to a trained astronomer, all those graphs there, every little peak, every little dip, is a signature, as you were showing earlier, of a particular chemical element. So we proved for the very first time that in the collision of neutron stars, a lot of the heavy element that you and I, pretty much everything we have around the house is made of, they are generated in the collision of neutron stars. Some of you may have heard that we think that a lot of the heavy elements are generated in explosion supernovae. That is true, but we have known for many decades that there aren't enough supernovae out there to explain all the heavy elements that we see in the universe. Neutron star collisions have been proved with this observation to be extremely efficient. And that's not surprising. What's more efficient than taking two big chunks of neutrons and smashing one into the other?
Yeah.
So that was one amazing result. And I think this is an incredible result that we obtained.
Well, what's fun about this also is a lot of the bling is made in these colliding neutron stars. If you want to have platinum, if you want to have gold, if you want to have these elements that people find precious, thank your neutron stars.
That's right.
Yeah.
If I recall, I remember hearing that it was like several Earth masses of gold were made during this.
Yeah,
or something.
several tens of Earth masses of gold and platinum. It's just too bad that's about 120 million light years away.
Yeah.
So we're going to need a way bigger rocket than the one they showed.
I'll get right on it.
Get right
if
on it.
anybody's
Go
got
on it.
$20 billion.
That's making on the cheap.
Yeah.
So here I want to stress again, the gravitational waves are not sounds, right? Of course, they're ripple, vibration, space and time. It just so happens that the frequency of the gravitational waves that are emitted by neutron stars and black holes, they happen to be in the few tens to 100 to 1,000 hertz. So the same frequencies as sounds that we can hear. So we can take the output of our detector, the really literally stretching and squeezing space-time, and convert it to sound that you can listen. So these low rumbles that you listen here is the background noise of our detector. But as time passes, you will see a bright line appearing that is moving, of course, to the right as the time passes, but it's also getting brighter and it's getting higher in frequency. This is again the two neutron stars getting closer and generating stronger gravitational waves, and then faster and faster. When we get very close to the end, if you listen carefully, you'll hear a little whoop of the two neutron stars colliding. So you have quite literally listened to sound made of gravitational waves that were produced 120 million years ago. They traveled across a big chunk of the universe and were detected by the LIGO instrument. So I think this is extremely exciting and cool. Of course, I'm biased because this is my work. But I wasn't the only one to think that this discovery was cool. So the LIGO laboratory, the LIGO observatories, and the three founders, the three people that came up with the idea and fought very hard to make LIGO a reality, won the 2017 Nobel Prize in Physics for the discovery of gravitational waves. It's sad that Ray Weiss passed just a month ago, but up until the last minute, it was always keeping track of what was happening, and every time there was some intervention, the observatory was always the first one to jump in, dress up, and get to the lab. So, but you know, this was a very important recognition and probably the best time in my entire career. So by now you might have a question. So how can LIGO even possibly detect such a small signals? I told you, something 1,000 the size of a proton, like monitoring here to Proxima Centauri with the precision of a human hair. Well, we use an instrument that has a very complicated name. It's called an interferometer. What it is that we take a laser, and a laser is a very precise source of light with a very precise wave, with a very precise light frequency. So we send it to a mirror, which is called a beam splitter, that splits this beam in half. Half will travel 4 kilometers one direction, be reflected back by a mirror, and the other half travels 4 kilometers, 2.5 miles in the orthogonal direction. When the two waves come back, you can tune the length of the two arms so that they cancel out, what we call destructive interference. So there's no light going there. But then now, when a gravitational wave comes by, it's going to stretch one direction and squeeze the other one. So one of the two beams will come back a little bit later because it's longer, and the other a little bit earlier. And so they don't cancel out each other. So this is an instrument that will take the fluctuation in space and time due to the gravitational waves and convert them into light. Sounds simple, right? Well, when people came up with this idea, they figured out that this is a great idea, but there's no way this instrument could be sensitive enough to get gravitational waves. You would need to make it a lot more sensitive. So instead of making it 4 kilometers long, you could make it 4,000 kilometers long. There's just a problem that it's hard to build something 4,000 kilometers long on Earth, especially because we will all agree that Earth doesn't quite look like that.
Yeah, it turns us into flat earthers, is what it does.
The other way would have been to just use a very powerful lasers, but we did not have, and we still don't have lasers that are that powerful, right? So it turns out that instead of using brute force, we had to be clever and smart. And so there's a lot of development and a lot of technique. So for example, instead of using only one mirror at the end, you add one more mirror. So the laser bounces multiple times back and forth. Instead of using a super powerful laser, you put what is called a power recycling laser, mirror, sorry, that's exactly what the name tells you, recycle the power of the laser. So this added complexity to an idea that was simple at the beginning, but made it possible to get to the sensitivity that we needed. So I would love to take you all now and visit the two observatories we have.
Let's go.
Let's go, all right.
Let's go.
The second best thing I can do is to show you a flyby. So we have two detectors. One is in Hanford, which is in eastern Washington State. You can see the desert area out there. The other one is in Louisiana, Livingston. So that building you see in the center is where the laser is generated and split in half. And then you see the 4 kilometers, 2.5 mile long concrete tube. Wow. That concrete tube is a protection for an actual steel tube that we have to use because all our instrument and our laser travels in vacuum. So we have to keep the air out. So everything is in vacuum. So if you wear the laser, you would see these multiple times, so bounce back and forth. And then you can see here a view of our central building. Each one of those big tanks, they're, again, vacuum tanks. We pump the air out, and our mirrors and our instrument are all inside to avoid contamination and vibration. So you might ask me, why do you have two detectors? Why one, in one corner, the other corner, the United States? Well, gravitational wave detectors like LIGO, they are omnidirectional, as we say. So they're sensitive to signal coming from any direction in the sky, which is great, because can you imagine the trouble we would have to go through to point something which is 4 by 4 kilometers? But the other, the flip coin of that is that one single instrument wouldn't be enough to tell us if from which direction of the sky the signal is coming. So we have to, and we do with our instrument, exactly what your brain is doing right now while listening to me. So we have two ears. Each of them is sensitive to sound coming from any direction. So you on that corner, your brain is measuring the slightly different time of arrival of my voice to your two ears, and you can tell that I am on your right. I hope I get this right. And same thing on the other side. So we do the same with our instrument. We can measure the few milliseconds different time of arrival of at the two observatories, and with that we can pinpoint where in the sky the signal came from. You can imagine that there's a lot of technology, advanced technology, that goes into reaching those kind of sensitivity. There's a lot of optical engineering, mechanical engineering, electronic engineering, scientists that come up with the idea, technicians that build and maintain the thing. Everything needs to be in vacuum to avoid the contamination because of stuff in the air, but also contamination of the signal because of sound, vibrations, right? Our mirrors are made of the purest glass that you can even imagine. The coating we put on the surface reflects everything but 5 parts per million. So 99.9995, I always lost count of many nines there are there, right? So, but those mirrors, they need to be isolated from the motion of the ground, because the ground is always enough small earthquake that would be a million times louder than the signal we try to detect. So we use active and passive isolation system to maintain them isolated.
What do you do about trucks driving by?
Well, that's the thing. That mirror is probably in the most quiet place on Earth. So we do everything to make sure that all vibration from humans' activity, for example, is isolated. That's why we don't have that.
So you don't have a basketball court out there where
no.
Okay.
At some point, we even go as far as say we don't want to have tall trees because the wind will shake the trees.
Wow.
And the trees, the roots of the trees will shake the ground.
That's
you
crazy.
can see that.
Can I ask though, wasn't there years ago interference from people using microwave ovens to heat their lunch?
That was a different,
that was a different story.
That's a different.
That's fast radio bursts.
Yeah.
Okay, I'm sorry.
That's for radio
Yeah, that would-
telescopes. Yeah.
That wouldn't do it.
But for example, we have problems for people logging trees around the section in Louisiana. So sometimes we have to stand down because they're logging too close to our area, and big trucks and big logging machine falling trees, that can be a problem, right?
Yeah.
And you'll be the first one to find out the super gator when it anyway.
Oh yes.
And are any long-range detection of earthquakes ever?
So our instruments are probably the most sensitive seismometers.
Yes,
Every time there's a big earthquake,
Kamchatka
we
recently, or
have.
places
There was a
like that.
7.8, I think, today.
Yeah.
I
Yes.
forgot where. So that took us down for several hours because the Earth is like a tuning fork and keep ringing for hours and hours and hours. So at some point the ground shakes too much and we have to stand down and wait it out because there's not much we can do.
That makes sense.
So 10 years ago, we had the very first discovery of gravitational waves. So the way we operate is that we build our detector, we improve the sensitivity, and at some point we say, okay guys, stop fiddling with the detector, we got to turn them on and start listening to the universe. When we do that, we go into something which is called an observing run. So we did 4 so far. So the first one was back in 2015, and we detected 3 signals from gravitational waves, including the very first famous one. Then we improved our detector. The second run, we got 8 signals. Then we improved it quite a lot, and we got 79 in the third run. Then now we are still going on with the 4th observing run. We have another couple of months before we shut down and we install more improvement. And we got 128 signals, mostly from binary black holes, already released like about 3-4 weeks ago. And then we have a running count about 109 as of this morning. I haven't checked. I have an alert on my phone that tells me when this new signal is detected. Might have been very well happened one during this. But you see, we keep improving our sensitivity to be able to reach farther and farther in the universe. And those 10 years have been very successful. And we learned a lot from the very first observation of black holes, proving that black holes actually behave as predicted by Einstein, seeing the collision of neutron stars, linking them to the generation of heavy element, all of that.
Yeah.
So what's coming in the future? But there's a lot more coming in the future. We are thinking, already designing or building the next generation detector, which is called Cosmic Explorer, because we reach so far in the universe that we won't see probably more collision of black holes because there weren't black holes, because there weren't stars yet at that time. Then we know that pulsars, as they spin around, they generate gravitational waves, so we expect to see that. We expect to see gravitational waves from the explosion of supernova, and to go back to even the biggest explosion of them all, which is the Big Bang. All these observations of gravitational waves could give us a hint of what dark matter is, because we need dark matter because of gravity, because of the mass. So here we are. We use gravity itself to measure them. We know that there must be some unification of quantum mechanics and gravity. Gravitational waves is the way to do that. At the end of the day, we learn how quantum mechanics work by smashing atoms and elementary particles together. Luckily, we cannot generate as much black holes together, but the universe is doing that for us. So that's a way to learn more about quantum gravity. And then there's always the unexpected out there, because all the best scientific discoveries were almost always the one that nobody was waiting for, nobody was expecting.
Yeah.
And so I'm pretty sure there will be some big surprises out there.
Yeah. The thing is, as a scientist, you want to experience this, wait, that's weird. that's when you know you're about ready to maybe make a discovery or find out somebody monkeyed with your instrument. But but it's the that's weird moment where you're going to have to figure out what made that happen. So those are the unexpected moments.
Yeah, the best time for any scientist is when the theory that you're trying to prove doesn't work. Because then you have a crack in the wall and you can start peeking through the crack and see what's behind.
Okay. I'm curious how much closer we are to potentially have an understanding of gravitational wave background.
Yes, so gravitational wave background, there are two kinds of backgrounds. One is what is called an astrophysical background, so all the binary black holes, the binary neutron stars out there, and we are probably very close to that. In the next decade or so, we should be able to get our detectors to be sensitive enough to see that confusion noise, all the popcorns popping. Then there's the gravitational waves from the Big Bang itself. It's the equivalent of the cosmic microwave background, but it's coming not for about 400,000 years after the Big Bang, but for the inflationary moment. So the very 10 to the minus 30 something seconds right after the Big Bang. We don't quite know enough about inflation to be able to say how intense that is. So it might be that we were going to be able to see something with the future generation of detectors, or that we will have to go with the Cosmic Explorer, or even better.
No.
But stay tuned. We'll see that eventually.
I'd imagine it's difficult to detect gravitational waves from the very early universe because don't they get stretched with the expansion of the universe, becoming longer and longer waves?
It's the same thing. Well, it's the same thing with the cosmic microwave background. Things that were very short wave is getting longer. But the model we have now is that inflation created almost a uniform spectrum of all frequencies. So there are long wavelength and short wavelength. The short wavelength at the time will be stretched, I should say, to the wavelength that we can observe.
Pick up. Okay. One thing that was amazing with those colliding neutron stars that I found fascinating was that confirmed the speed that gravitational waves travel.
Yeah.
Can you talk a little about
that?
Yeah,
that's actually very interesting because so those were generated 120 million light years away. So those waves traveled for 120 millions. So we saw first the gravitational wave signal, and 1.7 seconds later, Fermi detected the gamma ray burst.
Yeah.
Why 1.7 seconds? Because gravitational waves don't care about matter. They travel through any kind of matter as they want. So imagine the collision of two neutron stars. This cloud of gas that I mentioned earlier was very dense. There was a lot going on there. But gravitational waves didn't care, travel right out of it. But gamma rays, they're photons. They were continuing to absorb the re-emitted, all that matter. So it took all those photons 1.7 seconds to escape that. But this also means that we proved that gravitational waves and light travel at the same speed by a fraction with precision, which is 1.7 seconds over 120 million years.
Yeah,
so that's pretty good.
That's pretty good.
That's pretty good.
That's pretty good.
You mentioned Fermi, and I guess there's so much multi-messenger astronomy now. Yeah. I'm curious if that feeds into the refinement of your signal. You showed, for example, the difference in signal that we have now. How much does multi-messenger astronomy, for example, everything you get from Fermi, improve your signal or improve, the objects, the signal?
Yeah. So
can you refine it?
We don't quite refine the signal itself because if you want, we are the initiator of the multi-messenger astronomy. We detect, and then after we know that there was a strong signal, we can refine the parameters. But actually knowing more information from Fermi or from optical telescope radio allows us to learn a lot more about the astrophysics and what generated that. So, if there are black holes, so far we haven't seen any electromagnetic counterpart. No light was emitted, as expected. But it would be great to see something, because that means that those black holes weren't completely black, or there was stuff around them. But after the collision of the two neutron stars, we had all kinds of optical, infrared, X-ray, gamma ray, radio observation that allowed us to understand a lot more of the physics of what's happening there.
Right. And how can you differentiate between, for example, neutron-neutron star merger or an asymmetrical merger with a black hole and a neutron star? What's the essential tell?
So the bigger the object is in terms of mass, and the slower they move. So by just looking at the peak frequency, how high in frequency the signal is, you can tell what is the mass of the object. So big black holes, like the 30 solar masses black hole or even bigger, they typically get your signal up to 100, 200, maybe 300 Earth. neutron stars will go all the way to a couple of kilohertz, or even more.
Okay.
So by looking at the frequency, you can tell how big they are. And then it's even better than that, because then you know the masses. But then, once you know the masses, you know exactly what is the amplitude, how much energy those two black holes emitted. And then you can say, okay, how big was the signal when it got to Earth? And you compare to how big it should be, and that gives you a measurement of the distance, which is completely independent from anything else.
Right.
So that's why we are, or in this observation of neutron stars already gave a completely independent measurement of the Hubble constant, of the expansion of the universe. And you might have known that there is this big tension between two measurements of the Hubble constant, one which is using one technique, it's more local universe, and one using a different technique, which is more farther out, and they are incompatible by a significant amount. So our measurement, of course, falls right in the center, but the uncertainty is big enough that it's still compatible with both.
Okay.
But as we keep in the next several years, the more observation we have, the more we can shrink that error, and then we can see what happens there.
So place your bets now.
My bet is going to be right in the middle.
Right in the middle, you're going to stay where you are. We'll see.
But and I say that for the same reason we mentioned earlier, because if you confirm a previous measurement exactly, or you confirm an existing theory, then you don't learn a lot new.
Yeah.
If you have something completely new, then you have to find new physics to explain that.
So does anybody in our audience have a question? Yeah.
Would you go back a few slides to the chart of black hole detections over the past tip? That one. Why is that one yellow dot, like that high signal strength? Like, why is that the only one with such a high signal strength?
But it's still preliminary, it looks like.
Well, so that's that's depends on what the universe gives us, right? So the strength of a signal depends on how big the black holes are and how close they are. Just by chance, that was a fairly significant black hole size, and you see that's very low, so it's close. It's only 1 billion light years, which is relatively speaking, in universe distance, it's not that far.
Okay. Anyone else? Yeah, in the middle.
Could you maybe say in a different way what you said before about the relationship between the speed of a gravitational wave and the speed of light? I'm not sure I quite understood what you were getting at.
Yeah, so the prediction, our theory says that gravitational waves travel at the speed of light. So that's what was expected. And that is what was proven by this observation, because we first observed the collision on the two neutron stars, and we saw the gravitational wave signal, and then we saw a gamma ray burst that was generated in the collision. And they arrived on Earth within 1.7 seconds. So that means that those two signals, very different, gravitational waves, ripples in space and time, gamma ray burst, electromagnetic radiation, travel for about 120 million years, or million light years if you want to say, and they got here within 1.7 seconds. So they're basically essentially the same speed.
But I think he might have been asking about the difference in the perceived speed because of the fact that the gravitational waves don't care what's in the way. Isn't that what you said before?
Yeah, the other thing is that once both signals escaped the collision, they travel through empty space basically, and they travel at the speed of light. At the beginning, there was around the area of the collision, a strong, dense, relatively speaking, of course, dense gas cloud. So gravitational waves, they go through matter, doesn't matter, which is great, which is also our problem, because that's what makes it so difficult to detect them, right? But instead, photons, they are continuously absorbed by this gas. So those photons were, if you want, jumping around and trying to escape, but they were continuously slowed down by the gas.
Yeah, it was a local effect very near the neutron stars that had just merged. There was gas around them, and the gamma rays took that extra just under 2 seconds to get
just
through
some
that.
Sightseeing around the gas.
They hung out for an extra almost 2 seconds, hanging out there. So question up in the middle there.
Yeah,
and we'll go
this
over.
might be like a rabbit hole or a stupid question, but I just wanted to ask.
I always say there are no stupid questions, only stupid answers, but that's on me.
And lots of interesting rabbit holes. So bring it.
You've talked a lot about black holes. I wanted to maybe hear your thoughts about white holes.
So as far as I know, and mind me, I'm not an expert theorist on general relativity, I don't think there is any real solid theoretical prediction from white holes. So it's something that we love, somehow. So, well, if there are black holes, there must be white holes. This tendency that everything is black and white, right? But there's a lot of different things. So I don't think we really have any solid prediction of the existence of white holes with the current existing infrastructure and framework for how the universe works. So we haven't really seen any hint of anything like that, and we don't expect to see any. But then I would be love to be proven wrong, of course.
Some of the initial thoughts of white holes were very early on with the development of black holes, and it was folks that wanted to have sort of the amount of mass in the universe that you could get to be constant. So if stuff was being locked up in a black hole, they thought, well, could there be a fountain of material somewhere that's bringing material into the universe if it goes into the black hole? And we haven't seen any evidence of that, but that's from my knowledge of where that came from. But it was a very early on in the thought of black holes.
Early on, the existence of black holes were predicted in 1925, if I'm not mistaken, by Schwarzschild. But then, even at the time, people thought that was just a mathematical oddity. It wasn't impossible. You have to get to the 60 for Penrose, basically, and other astronomers to figure out that, okay, it is possible actually for a star to collapse and create a black hole. So for white holes, not only we don't have a way to create them, but we don't even have a theory that can explain their existence.
Can't explain them.
Do any of these detections tell us anything about the mass gap between the heaviest neutron stars and the lightest black holes?
So we have some evidence of some objects that were in that mass gap. So what were those? It's a very difficult question, because unless we can have an electromagnetic follow-up, it's difficult for us to tell if those are neutron stars or black holes, except the fact that black holes are sort of rigid. Neutron stars, they're more malleable. So when two neutron stars of two non-black holes objects, they collide, you see tidal effects. So that we are not quite sensitive enough to get to that level of details, but in the future we'll be able to get to the level of detail close enough to say, okay, two things that are about two solar masses, so borderline. Are they rigid as a black hole, or are they kind of soft, relatively speaking, as a neutron star?
Right. And on the other end, have there been any detections of supermassive black hole collisions?
So we got as far as up of a few hundred solar masses. So now, mind here, there's a bias here, because our detector is not very sensitive below, let's say, 20 to 10 hertz, because the vibration of the ground is way too much. So we cannot really observe any black hole that is any bigger than maybe 200-300 solar masses, maybe 500 solar masses at the most, right? So we see that we saw quite a lot of heavy black holes, so it doesn't look like there's any sharp cutoff on the distribution, but above a certain mass we cannot observe. That's where LISA, the laser interferometer space antenna, will come into play, because they will be able to observe much lower masses and much higher masses, much lower frequencies.
I imagine that the Vera Rubin telescope will be opening up frontiers, because you'll pick something up and it'll be able to take a huge chunk of the sky.
They are already on it. So we have already an agreement with them, and they're ready for any of our observations. There was an event a few weeks ago that could not be observed because they couldn't quite point to that area of the sky. But yeah, we are definitely, one of the reasons our observing run has been extended several months. It was supposed to end at the beginning of this year. We decided to extend almost to the end of this year to have a significant overlap with the first light of Vera Rubin.
Okay, fantastic.
Because they have an exceptional telescope that they can cover a big fraction of the sky.
Huge chunks of the sky can be covered in a night. So I think we had one more question we can cover from the audience. Anybody? Yeah, over here, Alan. Yeah, nice to see it.
Do you find that these gravitational waves approach the Earth from a particular direction more so than others, or they just come haphazardly anyway?
They come, as much as we can tell, from any direction. Remember that we are seeing stuff as far out as several billion light years, so we're really probing the whole universe. So we know from other observation that there's no reason to expect them to come from a specific direction. And so far, they're coming from any direction. Also, the fact that the two observatories are in the United States, and there's a lot of rock behind them, doesn't really matter for gravitational waves. There's no effect at all.
Yeah, and also just folks, other nations have built these detectors too, which helps us pinpoint the location of these even more. So are other nations joining the detection? So how many do we have now on Earth?
So we have those two LIGO observatories in the United States. We have the Virgo Observatory in Europe, in Italy. That's actually where I used to work before moving. You guys have already guessed that I'm Italian, but there's no way I can hide my accent, but that's where I used to work. So they have similar detector, a little bit shorter, it's 3 kilometers instead of 4. They're actually working with us. So a lot of the detection that you see here, at least from the third run on, the Virgo detector in Italy contributed. There's a similar detector being developed in Japan that is also 3 kilometers long. It's underground. There's some advantage of being underground because the earthquake a lot of earthquakes at least tend to stay on the surface of Earth. So going down underground is quieter. There's also a 600 meters long detector in Germany that was one of the very first detectors that served as a prototype to prototype a lot of the technology. And then they never managed to extend it to a full-scale instrument.
Yeah.
And just to tail end that, wasn't there a thought of having a space-based LIGO detector?
Yes, there is plans for the LISA detector, the Laser Interferometer Space Antenna, which is, I think, still a NASA and ESA collaboration, and is still planned, as far as I know, to be launched in the 2030s. I don't remember exactly the date.
Although, again, U.S. funding on that, we'll see.
We'll
see. That might be another one the Europeans take on themselves. We'll have to see. So, well, let's thank our guest again. Thank you so much for joining us. It's been fantastic. And we'll have you back. Well, we won't. Maybe we'll wait just another year.
For the 20 years of LIGO?
Well, not the 20 years, because we'll have you back sooner, but maybe for the next run when you clean things up even more.
That would be fantastic.
Discoveries keep being made, and it's just fantastic.
Yeah.
Well, tonight, folks, I want to end our program. Let's see, we'll get back to our stage computer. We want to end our program tonight with a little video that shows each of the drill samples taken by the Perseverance rover. It's about a minute long, and then we'll run our credits. So once again, I want to thank our guests. Thank you so much for joining me, Gabriele Vajente. And thank you, Laura Mayo-Braun, Ginger Rose Brucker, and also Jared Head, our panel. Thank you so much. And I'd like to thank our audience for joining us here in person, our YouTube audience at home. Thank you so much, everybody out there. Thanks to our tech crew, our production crew that helps make this possible. We'd like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. And as always, All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks. So we hope you enjoy this program, and come on back next month and join us. Thank you, everybody.